So hello everyone. So I'm Thomas LAUVAUX. Today I'm going to present, or I'm going to defend actually, my habilitation à diriger les recherches. The title of my presentation is Assimilation System for Atmospheric Greenhouse Gas Measurements from Continental to Urban Scales. So I'm going to present what I have done and what this field is about and my research project in the years to come, or at least what I envision to do. I'm going to go backward in time to the 80s, the late 80s or early 90s, with a key paper that actually started this whole field of atmospheric inversions, I think, in many ways. The identification of what we called at that time the missing sink. The idea was quite smart and quite simple, was to actually collect flash data around the world. So you can see here these codes, these acronyms you see on the right, or flash samples. So the process was quite complicated at the time. You had to sample air and get it to a complex machine. The whole process would take hours just to get a single point. So they would only collect few points per month, but they had this for all the latitudes and compare that to an atmospheric model. So the atmospheric model was typically a giant general circulation model where they coupled the emissions and the fluxes from the vegetation and the ocean. At the end, what they noticed was this overestimation from the model. And clearly, the only way to explain that was by adding a sink, absorbing carbon in the northern hemisphere. This led a lot of people to conclude that, okay, clearly we have a missing sink, most likely from the continental vegetation, because this is where most of the vegetation is located over the globe. This had a lot of debate until it was actually proven and went further into details, which part of the vegetation is absorbing CO2 around the world. It kept going with more advanced systems. So here I present you two major studies in the early 2000s, one by Philippe Bousquet, present here, using a global network of sensors. At that time, stations started to be continuous sensors, so you have more data, more locations collected, so more often. And the analysis led to trying to split that flux into regions. So you can see these big blocks. You can call them eco-regions or climate zones or whatever. They're defined by their vegetation type and their climate. So somehow they're supposed to be consistent. Not always true. You see the blocks are quite big, but in any ways, you start to see how it was decomposed into sub-blocks. So the tropics, the north, the south, and the total. You see also the uncertainties associated with each bar. So we started to see some of the signals, big absorption from the north, a source from the tropics, some absorption by the Southern Ocean, and a total for land and ocean. You see the very large uncertainty associated with the total land flux. So still more to be done. This evolved, and a recent paper by Sean Crowell, it's a whole group of people who actually use now the stations, as I showed you before, but also a satellite, where they compare different inversion systems. So the global budget over 2 years, you see the fluxes going up and down. So in the winter time, you release CO2 from the atmosphere, it's respiration mostly, and then you start to have a large uptake in the summer as the vegetation starts to grow. So this seasonality is there. You see that most inversion systems, so you start with a first guess. A vegetation model gives you a number close to 0, and then all the inversions converge towards a negative sink, a negative value, right? So an overall sink from the vegetation for the land. Now, when you start to break it up again, now you see again a wide uncertainty. So the South Tropics and the North Tropics, you see first that the red bar tends to disagree with the green and blue. So technically the surface stations tend to give you a different answer than what the satellite tells you. Here is the CO2 emission. Some systems found that it more or less agrees, but on average, across many inversions, you see that there is still disagreement. And the attribution is a big problem. You see that sometimes we say the Southern Tropics is actually a source of carbon or a sink. So it varies quite widely. So to understand what is really driving this absorption of carbon and this release of carbon at the global scale, it remains quite complex. So the idea was to zoom even more. So for example, I'm going to take one of the first studies trying to use a domain limited system. So this was Claire Carouge, PhD, the early 2000s, where she used actually a network of towers across Europe. You see how the network expanded. So we started with very few points in the 90s, and now we have about 20 stations just for Europe. And you see the area it covers. So it's not really fully Europe. It's actually a fraction of Western Europe. And she applied that system to Europe to try to see if we could converge. And we went even further because it's during the Carbo Europe project, very large initiative in the same thing, early 2000s. We started with an experiment that was on a very small area. You see the southwest of France here. We had only 2 towers in that area, but closely located, and aircraft flights. The aircraft were measuring the fluxes directly. We also had eddy flux towers located in agricultural areas in the pine forest to try to actually get a number for a very small area. Interestingly, we found convergence. So here I show you very quickly, we had 3 intensive periods. In black, you have the first estimate given by a vegetation model. In green, you can see now the inversion estimate. And the 2 red points give you the flux measurements. So these are direct flux measurements. They are not inversions. They're directly measuring at the surface what's going on, both from an aircraft and from an eddy flux site. So this was the first step to say, well, we might reach convergence when we go at finer and finer and finer scales. Okay, so that now I've introduced pretty much the idea of the global inversion and what we have seen, how we are zooming in more and more to get answers at the regional scale, at the local scale. The idea here be trying to reach convergence that we don't often see at the global scale. So I'm going to introduce you what is an inversion, and I'm not going to go as in a lecture, but give you the big ideas. I'm going to list some of the uncertainties because this is really where all the optimization relies on, uncertainties. And finally, how we reach now the scale of even the fossil fuel scale, which I call fossil fuel scale because you can imagine a city even smaller than a region. And then I'm going to present to you what I think would be the next step. I'll do that by theme and not the future will be in the middle of my presentation. I won't wait for the end of my presentation to talk about next steps. Okay, so let me start. Just to scare you a little, I put a couple equations. So this is the inversion cost function. Typically, it's exactly like a linear regression. You have some information, what we call in our jargon a priori, right? So we describe by that term. And on the other side, you have the observations, and you're trying to merge what you know from your model and what you have observed in the real world. Well, except that we measure concentrations and we estimate fluxes. So it's an indirect process. We need to link what we have seen in the atmosphere to retrieve what has happened at the surface. We're not measuring fluxes directly. So that's the so-called inversion process. You can get here the optimal solution. Okay, so if you can afford it, because it's quite heavy to compute, but this would be your optimal solution. Here, if you want to see graphically, this is what happens. We need an observation operator, meaning we need a link between the concentrations we measure and the fluxes we want to retrieve. The observations tell you something, your prior tells you something else, and you try to find the optimal solution between the two. At the same time, in some ways, consistent with what you thought you knew and what you have observed. Okay, so what does it mean for regional inversion? Well, you need to fill different components. You have different unknowns. You need a set of fluxes. You start with a guess. So you say, in my area, I think this is the map and over time and space. You need also fossil fuel because it's not only vegetation. There are some cities in the area I showed you. For example, we had Bordeaux, we had Toulouse. These are major cities. You cannot ignore that. And you also have boundaries. It's a box. So you need a boundary inflow. What comes in my domain over my area? For each box, we need to define uncertainties or errors. Sorry for this, that should be uncertainties. So you have the prior uncertainties for the fluxes. For fossil fuel, often we assume they're perfect. Not always for the urban scale, but for regional scale, that's what we do most often. And we also need boundary uncertainties. All of that is going to be combined into a transport model. So we're going to simulate what happens in the atmosphere. You have the full field of concentrations that you are going to compare to your observations. So for example, you simulate CO2 that, like in my very first example, is higher than what you observed. You have to decrease the emissions or increase the uptake. You need to compensate for what doesn't match with the atmospheric observations. At the end, the optimal solution, we call that posterior, you could call that optimal or inverse CO2 fluxes. So that's nothing else than the best combination of what you have observed in the atmosphere and what you have assumed in your model initially. So does it work? Because I showed you some examples, but if you, for example, take the Corn Belt, this was the mid-continent intensive experiment. There were about 10 sensors around the Corn Belt of the United States. You see here this intensive corn area, which feeds most of the cows in North America. The idea was to run an inversion and see if we can agree with the official inventory. The inventories are following guidelines, meaning they take all the harvest grain, They calculate the carbon content, the water content. They have a lot of complicated estimates for each field, for each county, and then they come up with a total for the area. We had 3 inversions and 1 inventory. I show you all of them here as a distribution. Carbon tracker, which is a global inversion, quite common and used by many people over the years. The inventory, which had a full Monte Carlo uncertainty analysis. So you see it's not a Gaussian, it's actually a non-Gaussian distribution right there. And then 2 regional inversions, one made by Colorado State and mine in the back at Penn State at that time. We all agree, statistically, that's the first good result. So we were very, very happy with that. However, it's still a very large uncertainty because this is the largest sink over North America. It's about 100 teragram of carbon in that little box, which is quite significant. It might be about 1/5 of the entire North American sink. And you see that the error bars are significant, even for the inventory. So we do have a certain degree of convergence, but still quite large error bars. If you look at the global inversion, you barely see the Gaussian because it's too wide to be seen on that plot. Okay, so now if we go for even more inversions put together and compared to also vegetation models, this is an example over Europe. It's about 1/2 petagram, so 500 teragram of carbon. If you remember the last example, about 120 just for the Midwest, and 500 for the entire European domain. And you see that, yes, it varies widely. It goes from a sink to a source. In general, the inversions tend to be a little deeper as a sink. They absorb more carbon. You see about 0.6 teragram for petagram, sorry, for many of them. The vegetation models tend to be lower, except one, VPRM. It's not a process-based model. It doesn't have a carbon pool, so some might say it's not maybe the best estimate to look at as it is out of the box. And then here you see the seasonality. So overall, yes, we agree, the phenology looks alike, which is the first result, but you see that the magnitude of the seasonal cycle varies widely. It goes from a very deep sink in the summer to a very small one in some solutions. So we still have some agreement, no doubt there, but the magnitude of that sink remains still under constraint by all these systems. Okay, so why that? And that's the question. Why are we, these inversion systems cannot converge? So it's because there were many sources of uncertainties. First of all, the big one that we often talk about is the transport errors. We assume to have perfect model because in the Bayesian system, we assume that we have observed the concentrations. We have some knowledge of the flux, but the link between the two has to be unbiased. That's one of the assumptions we make when we do these Bayesian inversions. We also have others. We need to describe the uncertainties, and it's not trivial. The prior fluxes, for example, you need to know the magnitude of the uncertainties, but you also need to know how they're correlated in space and time. Does a forest behave as a block very similar, or do we have a lot of variability within the forest? So when we see a problem and we correct one area, should we correct the rest of the area by the same amount? So these are all very tricky to actually define. We also have the boundary inflow errors, which are not trivial either. We use global scale models to feed our limited domain inversions. So sometimes these models are wrong, basically. And so we introduce a biased boundary inflow into a limited domain. So the transport errors, we need not only to describe their variance, but also the structures, which is also, it varies quite rapidly on an hourly basis. And finally, the measurement errors. I mean, most often they're negligible because we are doing so poorly on the other two that we tend to ignore these measurement errors. It's not always true because for satellites, for example, where they become more and more significant. So when I say most often, it's not all the time, but at least for in situ, we usually ignore them. So this is how it looks like if you run the model, and this is a very simple example. This is the same Midwest example. 3 towers, you run the model using different physics, different driver data. When I say physics, I'm talking about planetary boundary layer, surface scheme, the cumulus parameterization, the microphysics, the convective convection schemes. And you have that blue spread. You see, and the red is the observation. You see that in most cases, just because of the transport errors, we were able to explain the mismatch between the model and the observations. This is about 20 to 30 days, about a month. It's the month of June 2016. You see that most of the time, you don't need to adjust your fluxes. Your transport errors alone can explain the disagreement between the model and the observations. So they can be quite significant. Further, even more complicated than that, the convection is quite complex. We measure at a given altitude. So here I show you a transect. This is a cut. I sliced my model over North America from the west, here at about minus 120 degrees, to the east coast of the US. And you see how the CO2 is lifted up by the convection. Here it's an intensive convective event. I mean, it's pretty intense. We did that on purpose. And you see how the CO2, in a case where it's coupled, can go up to 10 kilometers to the tropopause, more or less, where here without the convection, you can have all the CO2 trapped in your planetary boundary layer. So the distribution in the vertical also matters. And we lack observations. We don't have a lot of observations of the full column. So we're not totally sure which model is right and which model is wrong. So if I go back to my problem, it's technically a box, and it's nothing else than a box, where you have the boundary inflow coming from outside. We need to define it. And then we have the surface fluxes, the amount we want to estimate. It's really what we care about. The boundary inflow in a perfect world should be known, but unfortunately, it's not exactly known. So I show you the typical flow over North America. You have the jet stream, so advecting air masses from the west coast to the east coast. It actually moves in the winter time going south and summer going north. And you have on top of that circulation from the Gulf of Mexico. So in the summer, for example, what the North American monsoon, not very famous actually, but there is a monsoon in North America, bringing air masses from the south, sucked by the jet and pushed eastward by the flow. Along that jet, which is really, this is actually on an average scale, but if you look on a daily basis, you have these storm systems developing. So typically you have a cold front and a warm front moving. It's not the jet creating that, but they form along that jet, and they bring the air from the south up to towards the north, while they push air masses from Canada actually towards the east. So you have these completely different air masses confronting each other from the high latitude and the Gulf of Mexico mixing up at a location over the Midwest. So you can decompose that signal. If you look at the time series, what you will see is actually the low frequency. So these are from global models where you see the CO2 going up in the winter, pushed from the high latitudes, going in the summer, you have the uptake, so your CO2 decreases. But on top of that, you have that synoptic variability. So you see these very high frequency events that keep affecting what you call boundary inflow. This is on top of the surface fluxes. So you imagine that these little changes should be known if you want to actually get the fluxes that are behind that. And just to convince you that it's all about the meteorology, I show on the right the potential temperature. So when you have a cold front passing over, typically your potential temperature is going to drop very sharply. The cold air mass is going to suddenly decrease your temperature. So you see how they're completely correlated with the CO2 over time. Every time the cold air masses come in, you have air from Canada suddenly that you are measuring. 2 hours before, you were measuring air from the Gulf of Mexico, and suddenly you switch from getting these air masses from a completely different location. Okay, so I'm going to summarize because there are a lot of sources of uncertainties. I'm not going to talk about all of them. It could take a whole day. So we have, to simplify, we have the biosphere, what we're looking at, right? We have the boundary inflow, we have the transport errors, and we have the fossil fuel. Well, we try to put them all in one box. So to do that, you need to run an ensemble of boundary conditions, an ensemble of biospheric fluxes, of transport. You can run your model several times using different configurations, and you can use different fossil fuel estimates. And what we did, we looked at the variability, the uncertainties associated with each of them at different time scale. Because if you look at a 1 day, it's very different than if you look at a 1 year event, as you can imagine. So when you start, technically you're dominated by the biogenic. The transport is quite significant. And the boundaries and the fossil fuel come after that. But as you start to average over time, so if you want to look at the fluxes over a week, for example, over 7 days, your transport error significantly decreased. Well, because that variability I just showed you, day by day, is kind of smoothed. So suddenly your variability decreases. And you can keep on going and going until you get to the annual scale, which is typically what we're looking at for long-term climate prediction. We want to know if our annual budget is right. And you see the image, it's quite interesting because your fossil fuel is still actually a significant one, which you remember at the beginning, I told you we assume most of the time that we know the fossil fuel emissions. So this was one of the first surprise we had. The biosphere is significant, but about the same scale as the fossil fuel in that case over North America. The transport errors decrease significantly. Is that real? Are we missing some of the transport errors? Possibly. possibly. We can only run an ensemble that has X members. We cannot run 500 members. We cannot try all the configurations possible, and we may have missed some of them. But as far as we can tell, it's not a significant source of uncertainties compared to others. And finally, the boundary inflow. It's interesting that if you look at the boundary inflow, you almost drop to zero at the end of the year. We think it's because we are using global inversions. So when you use a global inversion, it's constrained by the annual observations. So all the global inversions agree on the annual growth rate. So we think they all agree at that rate. As soon as you start to look at more details at the seasonal time scale, then the global models tend to disagree more and more. And then you get that nearly stable inflow error that you get. Okay, so next step. I think now that we have discussed a lot about the carbon estimates, can we converge? Are we in agreement between the vegetation models, the inversions? What I'd like to do in the coming years is to go instead into processes. So why processes? Because technically you don't really need to know the fluxes. If you could tell that your vegetation models have the processes right, you can use them for your climate projection. So here is an idea that we developed with the CASA model. It's a vegetation model. We run over North America. We run many versions of CASA with different parameters. So to test them, we took the AmeriFlux tower network. So you see these are a lot of flux towers. They measure fluxes every 30 minutes. They give you a flux estimate. And for different ecosystems, we try to see if CASA could reproduce the uncertainty associated with the model data mismatch. You see in some cases it seems to work okay. So meaning that the model spread includes the observations. In some cases it doesn't. We're completely off. The seasonal cycle might be off. So we know it's a first attempt. We know it's not perfect, but we have tried to represent that spread. You see, it's the yellow curves you see here on the plots. Okay, and what happened is we took that CASA model with all these different runs and we put them in our transport model. And we looked at the mixing ratios. And so for each kind of configuration, we can see how far we are from the data. When you do that, it means you can now see for different values of different parameters, which one seems to fit best and which one seems to fit worse. So now we have ranked them depending on their scores. And we started to identify, for example, the light use efficiency optimal value or the Q10, their respiration value from the model standpoint. We also looked at the eddy flux measurements and see if we went to the same conclusion. And yes, we did. The ranking was about similar. So this was a very interesting result for us. It means from an eddy flux standpoint, you look at the flux towers or you look at the atmospheric towers, we came up with the same conclusion. We found out that the light use efficiency value were about middle range. We found the Q10 values that varied, but so we could now define more or less which parameters for different ecosystems seem to give you the best condition. Now this is one model over one continent, right? So I'm not going to say that we have solved the problem at all. CASA might not have all the processes, and we might compensate the missing process by changing our parameter values. But at least now we're starting to get into the model parameters instead of looking at a carbon flux total that we can't really explain why we're too high or why we're too low. Okay, and now I'm going to move even to finer scales. And you could say, why? Why moving to the next step into the urban inversion where we have not fixed the issues at the regional scale? I think that's a genuine question, and you can totally wonder that. I want to go back to the total flux over the globe. So I told you about that vegetation sink that we discussed a lot, but the key player in that remains the fossil fuel emissions. This, you can see the growth rate of the observed atmospheric CO2 in the atmosphere, and actually the growth rate also of the fluxes, the emissions. So we keep increasing our fossil fuel emissions every year. And that's really what we need to decrease in the long run. So the idea is, and I showed you, the fossil fuel emissions are not well known. There's still uncertainties associated with these fossil fuel sources. So now, if we want to look at them, it's complicated because these emissions come from very specific areas, from a city, from a power plant. These are very, very small at the surface of the globe. So you can't run your typical global inversion at 1 degree resolution and hope that you're going to see a power plant. You need to go down to a kilometer resolution or even sub-kilometric resolution. Why do we do that, and why are these uncertain? I'm showing you an example here of cities. For example, cities report their emissions. They have these protocols, and every year they give you an estimate. So we evaluated over North America how good are these fossil fuel estimates reported by cities. we found a systematic underestimation of up to 30% on average, 16 to 30%. The errors, the uncertainties is even larger. And you can see that some cities are right on, some cities completely, some cities underestimate, some cities overestimate. On average, it's an underestimation, but there is a wide range of values and results depending on how they did it, which protocol they used. So this is the landscape of protocols and organizations that, for example, you can contact or you can follow the guidelines to get your city total. And that's why these fossil fuel emissions are so uncertain. There are many ways and many reasons to do it in different ways. So it started in the 90s with the first protocol to say, you take the number of cars and you multiply by that number and you get your total for traffic. The next one said, no, you don't take the number of cars, you take the number of miles you have actually run and you tell me if it's a truck or a car. So all these protocols go on and on and on and on. And this is where how we ended up with this wide range of values and estimates. So we want to help actually to get the fossil fuel emissions more accurately. The idea started in 2010, I think. So at the same time as the Paris network started, we deployed the Indianapolis network. So this is a network of sensors, exactly what I've showed you over the globe. Now we do it at the scale of a single city. You see here the different sites around the city. It's a Midwest, so you're surrounded by corn and soybean. There is a beltway around the city. It's pretty flat and wide. The suburban areas are quite spread out. You have a tower to get the upwind, so you know what's coming over your city, the CO2 coming over, and then you measure what's coming out. So it's exactly like a mass balance experiment. You know what's coming in, you know what's coming out. The difference between the two gives you what has been emitted by Indianapolis. And this is what we found. Well, if you take the inventory from the city, you get these green stars, quite low, 35%, about 35% lower than the high resolution inventories we developed. The inversions, only available for 2 years at this point, agreed pretty well with the high resolution inventories. I'm not going to go deeper into details, but we seem to agree quite well on the annual totals. So we confirmed the fact that yes, Indianapolis City is also, as many other cities across the US, underestimated their emissions. You see here what is called the city of Indianapolis. So I wanted just to illustrate there what I call the governance problem. The city of Indianapolis is a crazy line. It's a crazy area that has been defined for political reasons, by history. You see the county line, but it doesn't include the entire county. The county would be that square in the middle. So you also see what is from the city and what is not. You see, I use the term scope 1 and scope 2. Scope 1 being the direct emissions from the city, like a car. Scope 2 being the energy you bought. So for example, you need electricity, you buy it from the power plant, but the power plant is not in Indianapolis. What, do you include it or not? In scope 1, you don't, in scope 2, you do. So the city also disagrees on exactly what is scope 1 and scope 2 and how you should include it in your own total. So these are all the sorts of disagreements we found on these estimates and why we cannot also converge at the end of the day. Let's go into Paris. What happened into Paris was interesting. Recently, we had the confinement. So same idea, a network of sensors over Paris. And here I show you an inventory to the right. An inventory made by Origins Earth, a company that actually collected a lot of different data, activity data, fuel consumption, fuel energy production, building occupancy, heating, etc. And you see the different components. During the confinement in 2020, sorry, it's not last year, it's the year before, you see the decrease in traffic for sure during the first confinement, massive, a little less noticeable in the second confinement. You see the impact on building heat. Some industries also stopped. It's not actually very large. You see there is a small decrease. The idea here was to use it as a test bed. Can we actually use that confinement, see what the inventory says, and see what the atmospheric system would see? So Jinghui Lian, here, former PhD at LSC and now working at Origins, did that work. And she computed for the Ile-de-France area. So you have to crop what you think is Paris. Again, there is Paris proper. You see this little red spot. It doesn't match at all what is Paris. Paris extends way beyond Paris city limits. So we have a different flavor of what we call Paris. Anyway, she computed using a reference year. Your reference year could be 2018, it could be 2019, that's up to you. And you see that it does make a difference when you use it as a reference, for sure. The decrease looks much larger when you use 2019 as a reference year. But anyway, and she computed her own estimate of what the confinement impact was. It's about a 40 to 50% reduction in CO2 emission, in line with the official inventory estimate. So that was a nice result that we were very pleased about. The second lockdown was actually much smaller, 20% only. It's quite consistent with the fact that the schools were still open during the second confinement. It was less restrictive than the first one. So this was a demonstration that in a matter of a few weeks, you can actually have an estimate of something that happened compared to an inventory that often takes a couple years before you get the official estimate from the reporting. It takes time to compile all the data. So the inversion brings you, one advantage is the speed at which you can get the information. Okay, what are the next steps finally in all that? So we started to do this full inversion network. It seems to work over several years. We can get some short-term information, so major changes. So if you imagine there is a policy in place or they shut down a major source in the area, we should be able to see it and track it. So we should be able to help cities to accurately report. Well, we need to go further into other gases. So I've been completely obsessed on greenhouse gases, but there are other species that can give us information. For example, reactive species. I show you here from two different inventories how CO2 and NOx are directly related, where it's a combustion process. So when you turn on your car, you burn and you release CO2, but you also do release NOx and you release CO. So all these gases can actually give you extra information. So the idea of the years to come is actually to link these two gases. Well, it's not that trivial. First of all, you need to have measurements. We're lacking collocated measurements. So we're deploying now, for example, over Paris and over a couple other cities in Europe, we try to co-locate air quality stations with greenhouse gas stations. If you talk about NOx, we also talk about active chemistry. And so far, everything I've shown you has assumed that CO2 is passive. There is no chemistry. Chemistry will be another line in my list of uncertainty sources. I show you also why I want to go there. I show you here two inventories. The left column is the local AP, what I call is a local inventory. The one to the right is a regional inventory. And you see for the three different gases, CO, CO2, and NOx, how they distribute the sectoral contributions differently. They don't agree with each other. Some inventories put it more in the residential or tertiary, for example, for CO2. Some put it more in the traffic, the on-road. Some put it more in the waste or the combustion of energy. So you can really see that these protocols don't end up with the same solutions. We need to find actually what is the right answer, because the cities need to know where the CO2 is coming from, where the NOx are coming from, or the CO, to take actually actions on these. Otherwise, depending on who you believe, you might spend your money on on-road traffic first, or on the residential sector first. So these are really important, actually, decisions to be made by cities. And the future is also more integrated network. I show you here an example from the ICOS cities, the POL project. This project will actually deploy sensors over Paris, Munich, Zurich. We need more co-located sensors. Often we don't have a Flux tower where we have the atmospheric towers, or we had few aircraft flights over the city, but no towers to check it. We didn't have the inventories to go along with our atmospheric network. So we need to combine and make these super networks to really understand the uncertainty sources, what is wrong, what works, what doesn't. So this is really, for me, the next step in our system. Okay, I'm going to try to move quick because I'm still halfway. The Spaceborne Instruments. I showed you a lot of these networks. They are nice, but we're not going to cover the world with stations. It's too complicated. There are countries where it's going to take years, decades before we can actually cover all the surfaces we need to look at. So in the recent years, in the last, I would say 10 years, there was an increase in number of space missions. I'm showing you here a nice illustration of the International Space Station because there is a sensor on it called OCO3 that has been flying for more than 2 years now around the globe collecting information. So the first try I made, at least for the urban application, was to use the OCO2 data. You see that little track, this very thin swath on the ground. You see that track is a satellite. When you're lucky, your satellite passed near a city downwind. On that one, for example, the first image I show you, you see the track is almost lined up with the city plume. What you see is the CO2 coming out of Riyadh in Saudi Arabia. Some days you're very lucky. The plume is crossing your track of the satellite. So on these days, we can try to recover the emissions. So you see the example here. The plume has been cut. We have the model results. We have the observations. And with that, you hope that maybe you can get the emissions. Well, it does work when you have a good track, but unfortunately, you have very few good tracks. It's about 4 tracks per year per city. So you can imagine, you have 4 snapshots of the emissions, and you're trying to get an annual total with that. We're not trying to. We're just testing how it could work in the future. The next generation was OCO3. It's about this. It's the same instrument, same characteristics, except that it has a pointing capacity. So you can actually take the instrument and scan. So here I show you a scan over Washington, DC, and Baltimore. You see these bands. So the satellite, as it's passing over Washington, is going to make several bands to do some sort of a pseudo image. It's not a complete image for sure, but it gives you a better idea of the spatial distribution of the CO2. So for each time we had an image like that, we don't have hundreds of them. We have only few for each city. We try to run the model, simulate the plume, and see if we can match between the two. To a certain extent, we do have a beginning of an agreement, and you can see the plume location. Okay, the large values for CO2, the peaks are co-located. Some are completely missing in the model. So are we missing a source completely, or is the transport wrong? That's always a question. You see also what happens from space. You see this image. I was always shocked the first time I saw that. You cannot see Washington, DC, or Baltimore in that image. It's really difficult. What you see is a giant plume coming from New York City and Philadelphia. That's what you see. So the east coast of the US is an extremely densely populated area. We see more signals coming from outside our domain than inside in that case. On some days, you see a plume from Washington, DC, but on most days, you see the plume from New York crossing your domain. I'm going to switch a little topic, but it's exactly the same idea. Methane emissions. From the same satellite views and aircraft view, you can apply it to methane. I've been focusing a lot on oil and gas. Oil and gas because of that fancy illustration from the Britannic Encyclopedia. It's fracking. Fracking has been a new technology, I mean, a combination of several technologies, and it actually allowed for new production of gas, especially in the US. This actually led to the complete shift. Natural gas became really the main source of energy in North America, and keeps increasing. The idea is you drill, you frack the rock, you explode it, and the gas comes back in bursts that you then can put in the pipeline and burn. It's so big and so much concern because the installations it's billions of dollars invested in massive infrastructure. We start to doubt that these infrastructures are perfect. They might leak. And the Biden administration moved to limit methane. So why suddenly that move by the administration? Well, because every time we looked at, and top-down means inversion here, every time we had an aircraft flights or tower system or a drone flying over, we found an underestimation by the inventories. The bottom up, what we call bottom up, the inventories systematically underestimate by a factor of 2 to 3 the natural gas emissions. So interestingly, you can look at where it comes from. We took the Tropomi satellite, and every time a Tropomi is flying across the world, it gives you maps of methane. Here, I show you examples. When you look at these maps, first of all, you see clouds, right? These are the white pixels, and these are different snapshots across in the area. You see these little plumes in the middle. You see these yellow spots you can detect. These are, in fact, giant leaks over oil and gas infrastructure. When I say giant, I'm talking about 25 tons of methane per hour. So it's an open pipeline pouring methane straight into the air. So the idea was to take all these little plumes, all these little detection, and get an estimate of the emissions associated with that. So how do you do that? Where every time you have an image, you see actually these plumes, you run a model. Here is a Lagrangian model. You see if the wind was right. You see if the plume direction seems to match. So sometimes when we see that the wind direction was incorrect in our model, we just don't get an estimate. We reject it. But when things went well, your wind direction and wind speed is good, you get a plume, and you can get an emission estimate. This is the map you can make over 2 years. About 1,000 ultra emitters detected. If you zoom in, you can see that they follow the pipelines, they follow the infrastructures. They're mostly located in producing countries, meaning Russia, Turkmenistan, the Middle East in general, Algeria, North America. You can see directly the oil and gas infrastructure around the world. If you actually take the total of all these leaks alone, they're about 10% of all the methane emissions from oil and gas. Just these few giant leaks that we have discovered, detected on the satellite images. And we know we are only looking at the tip of the icebergs because the detection threshold is really high. 25 ton is quite high. So if you take other instruments like Sentinel-2, another satellite that's much higher resolution, you start to see smaller leaks. And you can put them on a log scale, and you can actually look at the distribution of your leaks. The blue ones are my very high leaks here, my super emitters in blue. In the middle, you now see the smaller ones from Sentinel-2. So they still line up, but you see how many they are. And you can go even into aircraft campaigns, and you can keep going on and on and on and on. When I showed you the 10%, this is only these top blue points. But we know there are many more leaks behind that we need to detect. The nice thing about that for the years to come, and we just started to touch Sentinel-2, is now if you look at these images to the left, you see the precision of it. We can now tell the exact well or the exact infrastructure or asset that leaked. We can tell the day, and we can try to associate it with actually a maintenance operation, a specific event, an accidental release. Just to let you know, but most of these releases are maintenance operations. And that's what we have found from Sentinel-5. Very rarely, these are accidental releases. I would say about 80% of them are actually maintenance operations. So meaning you need to fix something, you open the pipe, it leaks for several hours, you do your maintenance operation, and you close the pipe again. Okay, I'm gonna stop there and maybe not go all the way to all this conclusion, but maybe to go quick, I would say for the regional inversion, we still need to keep going because we need to understand how the vegetation is responding to the changes. And I didn't show you today, but yeah, there's the fertilization effect. Vegetation is changing. We need to see if our vegetation models are able to get the right the processes to see how they respond to climate change. For urban, to me, it's really the sectoral emissions. They're still out of reach. We cannot really see sectoral emissions with an inversion, and inventories are not accurate enough to give you the exact sectoral totals. But if you're a policymaker, you need to know your sectoral emissions. Otherwise, you don't know where to act and how to act if you want to reduce your emissions. For satellite, I think it's quite promising. We have seen things we've never seen before, especially in oil and gas, but also from space. We have discovered power plant emissions that sometimes were missing from databases. So we can do a lot with satellites. Now, that being said, data frequency, we don't have a lot of data, and precision are still roadblocks. So can we really reach the policy level goals? Can you get to like a 5% uncertainty on the city with a satellite? This remains an open question, and I don't think we have demonstrated yet that we can do it. Finally, the oil and gas is interesting because people are moving. Losing gas means losing money. So if there is a low-hanging fruit, I would say, in terms of climate policy, it's clearly methane. And that's why the last COP has been really talking a lot about methane emission. That being said, we need to go to high-resolution imagers because if you want to act, if you want to stop these leaks, you need to know which facility is leaking, which operations actually created that leak and released the methane in the atmosphere. It's not about the global total. It's really about the facility level attribution. That is the key to that. Okay, and I'm not going to put all the logos, but there are many of them. These are work done in North America, sponsored by different funding agencies, but also a lot by LSE. I started there 15 years ago, and I was really glad to come back and still work with my colleagues. Thanks to the graduate students, I didn't cite everybody, and the early career scientists, I didn't cite, but you've seen the name on the paper. I hope I didn't hurt any of them, but a lot of this is not my work, it's not by other people. And thanks to the members of the jury for accepting to review that HDR.